proportional controller design. So now we're finally going to put all of this together and design a controller to meet some design criteria, okay? And that's like where we're trying to be. Now, so this is the first of as many lectures that I can fit in till next Wednesday, I guess, on different controller types of controller designs. Proportional is the baseline for all of the ones we're going to do. We always start off with a proportional controller design. So this one's the foundational one, and then we're going to add some nuance in the future ones. So proportional controller design is the task of choosing the gain K with which the closed loop system performs in a desirable manner. All three performance classes, stability, transient response, and steady state error, can be affected by changes in the gain. However, with a gain controller, there's typically no way to satisfy strict requirements in all categories. So there's trade-offs, right? You're going to try to satisfy as much as you can, but you can't satisfy everything. Instead, typically stability can be satisfied and transient response characteristics can be partially satisfied. Varying the gain simply moves the closed loop poles along the root locus. However, often the root locus does not pass through the closed loop pole location required for ideal transient response performance. Later we will learn how to design controllers that do not have this limitation. So if we come back here and we look at this, we've got only root locus locations are possible by varying the gain. You can't make your closed loop pole be out there by varying the gain. You can if you use another controller technique that we'll learn, like when we get to PID control, we could make that happen. So, or at least we can get close. Okay, virtually always we assume it is a requirement for the closed loop pole to be stable. So we can immediately restrict our task to selecting those values of gain for which the system is stable. Recall from Chapter 3, the relationships between the location of closed loop poles and corresponding transient response performance. The parameters rise time, peak time, settling time, and percent overshoot can all be related to the dominant closed loop pole locations. Criteria will be given in terms of these transient response performance parameters, and the design task will be to choose the best gain, K, such that these requirements are met. So that's we're only going to be able to move along the root locus, but we're going to find the location on the root locus that is best for our design criteria. For most problems, we make the first or second order assumption for higher order systems and for first and second order systems with zeros. Recall that even if this is an inaccurate assumption, it gives us a starting point for design. So even if it's a bad assumption to make it a second order, assumption, it gives us a place to start, and we'll probably have to iterate on that. We will always simulate at the end to evaluate the actual performance criteria of a given design. So say you try it with the second order approximation, you're going to have maybe close to what your design criteria are asking of you, but you might have to tweak it. And so you might need to go back and change something a little bit and try it again to try to hone the gain. The following procedure is one way to go about designing a proportional controller. But let's keep in mind the adage that plans are useless, but planning is essential. Okay? So when you're coming down to it, we're going to try to use this procedure, but really it'll get weird when you actually get into the design. So this is the four steps. So using the first or second order assumption, estimate the ideal location of the closed loop poles for the desired transient response criteria. Then construct a root locus plot and select the location on the root locus that is closest to the desired closed loop pole location. Using a computer, ideally, but if not, using the methods from previous lecture to do it analytically or geometrically, determine to which value of gain K this location corresponds. So we look at the root locus, we say, okay, this maybe satisfies our rise time right here. This is where we want to be on the root locus. Or this is as close as we can get. therefore, we need to find what gain corresponds to that pole location. Using a, so yeah, great. So then step 3, solve for the closed loop transfer function with this gain. Step 4, simulate the response for a unit step command. Evaluate the performance criteria and iterate if necessary. So let's do it. Here's a plant with transfer function s plus 13, s plus 15. Notice, so what's the order of the system? First order system. Is it a first order system? Second order system. It's got 2 poles, right? Second order system. And then we've got how many poles, how many zeros? How many zeros are we going to have at infinity? How many zeros do we have that are finite? 2. So how many poles do we have? So how many zeros at infinity? 0. So let's do a quick root locus sketch here. Our poles are at s minus 2 and s so minus 2 and plus 2, both real. So just a little sketch. They would be like that. The zeros are at negative 13 and negative 15, right? Something like that. So if I was to do a little sketch, the root locus, starting out with our, far right real axis, marching leftward, locus, locus here, no locus, locus, no locus. So there's locus there and there. We know it has to be symmetric, so there's no ambiguity in terms of this thing's gotta go in some fashion from here to there. And that's our sketch of our root locus. So that's what we're looking at this. We're saying, okay, so for 0 gain, the system's going to be unstable. If you increase that gain, so open loop system's unstable. S minus 2 in the denominator means that we've got an unstable system when k equals 0. So if we increase the gain, we're going to get a stable system, which is good. We increase it to a certain point. We want this point to correspond to the performance criteria that we have, which is 20% overshoot. Remember, the percent overshoot is related to the damping only, right? Do you guys remember? I don't have the expression off the top of my head. It's not super easy, but there's a direct relationship between the damping ratio and the percent overshoot. And do you remember geometrically what the damping ratio corresponds to in terms of the complex plane here? Yeah, rays that go out in angles from the origin, right? So like a constant zeta, let's do gray line. A constant zeta line is a ray that goes out like this. This corresponds to some zeta. This corresponds to some other zeta, right? So when we say we want 20% overshoot, we're saying we want zeta equals something specific we can compute, right? So that's what our performance criteria is. So we're looking at probably there being 1, potentially 2, depending on how this circle goes, locations for the gain to satisfy that criterion. Okay, so it's good. It's good that we've got at least some possibility. If the root locus never crossed these lines, we'd never be able to get that percent overshoot on the second order approximation. Which this is not second order approximation exactly. This doesn't work because remember our second order approximation assumes there are no zeros. So we have got no finite zeros. So that's something that we think it'll just be approximate then. So it's a good approximation probably, but we'll see. Okay, so let's just move over to MATLAB then and see what we can make happen. Maybe some magic. Okay, so I'll work in the command window, and first I've got to define my system, right? I have it in this form of numerator, denominator, but they're already factored, so I already know where the zeros are and where the poles are, right? If it was in an unfactored polynomial form, I would use TF to put it in MATLAB, but since I've got it factored, I can read off the zeros and poles. I'll use ZPK. So sys equals ZPK. Our zeros are negative 13, negative 15, right? Our poles are negative 2, positive 2, and our gain k is just 1. So it should spit back out something that looks like what we put in. And it's always good to check it to make sure that you got the syntax right. You didn't switch poles and zeros or something like that. Okay, so now sys is that. No, I often call it sys, but you can call it anything you want. I think in the example, so I'm doing what we're doing here, but I'm just doing it live. But I call it G in here. Call it G, call it sys, call it whatever you want. You can just assign it a variable. So sys now, we can do things too. We want to do a root locus. So let's just naively open a new figure and say our locus of sys. And this is what we get, which is pretty cool. There's a nice thing you can do when you use our locus. You can add a grid, and it's smart enough to know that you're interested in damping ratios and natural frequencies. So it draws this radial grid for you, and it tells you the damping ratios corresponding to each of these rays, which is really nice. It knows what you want to do, so it's helping you out here. So we know that we want to be on one of these rays, but we haven't computed what that is yet. There is a, unfortunately, I didn't compute it, but you can go back to that formula for what zeta is. There's a shortcut though in MATLAB, which is that you can just use the data cursor, and it has that formula built in too, and it'll give you not just zeta but also percent overshoot. So 15.8% overshoot for this location. If I come down to, let's see, 15.8 was here. I want 20%. So if I move this direction on the curve, you can just arrow up and down. I have 19% overshoot with a gain of 0.248. And if I arrow down one, I have 22.4% overshoot for a gain of 0.197. So in between those two gains, so 0.197 and 0.248 is where I want to be. But there aren't enough points that are computed here for me to really know which or where in there to be, right? So, and then if I go down here on the curve, this one's kind of unique in that you can get back down to the 20% overshoot. But once again, we don't have the resolution to do it. So there are two locations that we can pick. Okay. Now, what do we do because we don't have enough resolution here? So what was that? Yeah, custom gain, right? Custom gain values. So our gain values that we used were just whatever the default was. So I want to say, okay, let's do, I like this idiom where we just plug in whatever we want in any order we want, and then it'll sort it for us. So sort. Let's put in log space. I know I want to be like less than 1 even, so really like log space 10 to the negative 3 to like 10. And then let's do like 100 points. And let's just even see, so this is a little bit, doing sort on this is kind of silly, but let's do that. Let's do our root locus again, but this time let's hand it our custom gains. So I just put a lot of points in there. And you can see that, well, oops, we're not necessarily perfect, but we've got probably more points in here to work with. So I can't get there from my current location. So what I might do is I'm going to get more specific. I'm going to say, all right, I want my gains to be, I want to go, I don't really worry about, I'm not going to worry about the whole thing. I'm just going to say I want to have good gains from from like say 0 to 1, and like I want like 200 of them. And then we'll do it again, and we will have more to work with here. So percent overshoot, 19.8 to 20.1. It's pretty close. So like between 0.2, so 0.231. Usually it's good to be a little bit on the like a little bit under for your guess. So 19.8 is here. It has a gain of 0.236. So let's say that. Let's say our K select is going to be, well, and I'll call it KP, our proportional gain, is going to be 0.23. What did I say? 6? Yeah, 0.236. That was what we selected based on our performance criteria. We could have selected one that's down here, and let's think about what would have happened if I had selected a gain down here. It would have matched my 20% overshoot. I would have to get more points in here to select it out. But what's different about a system that has dominant closed loop poles right here versus one that has them over here? We can try it later, but. Well, I think that we can get the same zeta value, so the same percent overshoot. But what other performance stuff is going to be affected? So settling time, right? So settling time, so if you move leftward with your closed loop poles, settling time decreases. So essentially the stuff that happens closer and closer to the imaginary axis takes longer and longer to happen. So if you select it in here, your percent overshoot would be met, but you would be slow. So we'll play with that. We'll choose a different game. We'll come back to it. Yeah.
So as far as assuming it behaves like a second order system, would that only matter if, for example, the 2 points were a lot and had huge distance between them?
So it won't behave like a second order system if you've got closed loop zeros that encroach on this area too much. If they're way out to the left, it'll be fine. But if they come in and encroach, which they probably will, it'll affect the second order approximation. So like this percent overshoot is an approximation. So that's why we're going to have to select it and then simulate it to see if it actually meets that criterion. So yeah, and then if you had polls, so that we had that like list of things that you can times when the assumption holds, like 5 times further out, like having the other poles or zeros be 5 times further to the left on the complex plane. That would be sort of a good condition for that assumption. But you're probably still going to make the assumption anyways, and then you're going to test it. Because we don't really have anywhere else to start if we don't start there, so we kind of just always make that approximation, even when it's really bad. Which oftentimes it could be off by like a factor of 2. But otherwise, you're pretty much stuck just guessing and checking. So you start with it anyways, and then you tweak. So let's do it. Let's choose a gain like we did, KP of 0.236. Now what our goal is to simulate it, right? So we have a system that we closed the loop using gain control. So we've got us, our system looks like this, right? We have our reference. We've got our gain controller that the error is going to come into, right? This is going to be the error. Our gain, that's going to go into the plant G, and then we're just going to have unity feedback in this case. So what we want is to simulate from R to Y, the closed loop response. So you could find the closed loop transfer function analytically and plug it into MATLAB. There's a shortcut though, because MATLAB knows what you're trying to do. So it has this nice function called feedback. And feedback says, oh, we know that you're going to do this a lot, so if you want to make a transfer function out of other transfer functions that has a feedback loop, you can just use this feedback function. So let's call it syscl closed loop is equal to feedback. So we have to look and see M1 is the forward is our plant and gain, and then M2 is the feedback loop. So our forward transfer function is going to be our gain KP times the open times G, right? And then sys2 is just 1. So that is our closed loop transfer function, and we can even have it printed out. And here's what it looks like. This is our feedback. So this is unity feedback, our closed loop transfer function. So now we can simulate with it. And what we care about for transient response performance, which percent overshoot is the step response, right? So let's open up a new figure and just use the step function to take a look. And for now I'll just do that. Okay, so step response looking pretty good, but we've got like 36% overshoot, right? So 20% was our goal. We missed by a little bit, right? So we don't know a priori, but we know from looking at the root locus plot that if you increase the gain, the percent overshoot should decrease. So let's increase the gain. So let's say that our KP now, so let's do this, but let's also say KP. Let's just like increment it by like 15% of the previous one. Okay, so there's our new closed loop transfer function. Let's do a step again on that. We're still getting a pretty large overshoot. So let's increase it again. Maybe we'll increase it a little faster because we're running out of time. And let's do the step again. Oh, we're getting closer, right? So we're at like 25% overshoot. So we need to increase it again. So notice this is what I told you. This is not a totally linear process. Let's just do it by 1.5 again. And we'll do the step. Okay, so we got under. now, right? So what's our KP that it ended up? 0.6. So we needed quite a bit of tweaking. Even after we used that second order assumption, we needed to use quite a bit of tweaking. That's okay, because we had a place to start, and then we could tweak from there. So I don't have time to go into the choosing the other gain, but the other gain we would have seen that instead of taking 1 second to settle down, it would have taken probably like 5-6 seconds to settle down. Okay? So that is our gain control demo. Let me know if you have any questions on that. So I got that original gain by looking at this. So
right, but like, so you said iteration and get a 0.3 something.
Yeah, and actually,
I ended up with a gain of like 25 something.
yeah. Well, you know, it's weird. I'm looking at it now, and I'm seeing. Was I looking at the wrong point?
See,
But I'm looking at it now, and I see that this is. Oh no, it says gain of 0.23. Yeah, that's how I started with it, right? I said percent overshoot is around 20%, and then our gain corresponding to that is 0.236. I'll come take a look.
those controllers and stuff.